Okay, there are many ways to work through this algebraically. We know kinetic energy is 1/2 mass velocity squared. So we need our kinetic energy in joules. This was 3.75 kilojoules, so I just multiplied by 1,000 to get 3,750 joules. A joule is a kilogram meter squared per second squared. So that's equal to 1/2 times the mass times my velocity in meters per second squared. So the first thing I did was to square this and get 27 meters squared per second squared. Then I am going to multiply this whole thing by 1/2, so I multiplied both sides by 2. So that's where my 2 came from. By multiplying this side by 2, multiplying this side by 2, I get rid of the 1/2, because 2 times 1/2 is 1. Then I have the mass times 27 meters squared per second squared, so I divided both sides by 27 meters squared per second squared. And I get the mass 280 kilograms. Does that answer your question? I just multiplied by 2 instead of dividing by 1/2. Okay, so that's the first equation, and you have to be able to know that equation and either solve for kinetic energy, solve for mass, or solve for velocity. And it's rearranging it using algebra once you know the equation. And you really have to watch the units because it's in joules and you need your mass in kilograms. So what I like to do to make the problems a little harder is to give you something maybe in grams, or maybe you'd have to change some other units for velocity into meters per second to make things a little bit more challenging. All right, now we want to talk about a property called heat capacity. It's an extensive property. Remember, when it says extensive, it means that it depends on the mass or on the size of the sample. So if we talk about heat capacity, heating up this bench, how much energy would it take to heat this bench up 1 degree C? I could measure that. But if I sawed the bench in half, the heat capacity would not be the same. It wouldn't take the same energy to heat half a bench up, right? So when we talk about heat capacity, we're talking about a particular object. And it has units of joules per degree C or kilojoules per degree C. And in the textbook, it says Q, the heat, is equal to C, the heat capacity, times delta T. I tend to just write it out in words. Heat capacity times the temperature change is heat. Now, the thing to notice, this is temperature change. It's not final temperature. It's not initial temperature. It's the change. So the first thing you're going to do in a lot of these problems is to find the temperature change. So we can do some really simple algebraic problems with this. How much heat is required to warm an object with a heat capacity of 25 joules per degree C from 2.5 degrees C to 10.0 degrees C? Well, the first thing that we do is we calculate the temperature change. And we know a temperature change, delta T, is T final minus T initial. So in this case, the final temperature is 10 degrees Celsius minus the 2.5 degrees starting temperature is a change in temperature of 7.5 degrees Celsius. That's my delta T. Now I can use that information to calculate the heat. I know that heat is equal to heat capacity times temperature change, delta T. So that is equal to 25.0 joules per degree C times the temperature change, 7.5 degrees C, is equal to 190 joules. And that's how much heat is required. So those are pretty straightforward problems. You're looking at the algebraic relationship and you're just multiplying by 2. Now, if we look on the next page, we find something that's a little bit more useful for us in a lot of situations. Heat capacity is extensive. It depends on size of the sample. So if you're trying to compare data between laboratories or between experiments, it's much harder because you can have different size samples. Specific heat is intensive. That means it's independent of size. So it describes how much heat it takes to change the temperature of 1 gram of substance 1 degrees. You could think of specific heat is equal to heat capacity per gram, is kind of what we're saying. And specific heats are information that's well documented and tabulated for you. And there is a table on page 260 in your book, or table 6.1. Also on page 6-8 in your note packet, I have included this table for you to make it easier for you to have it in class, because I know a lot of you don't carry your books. Okay, we can also do really simple problems with this relationship. The heat is equal to the mass times the specific heat times delta T. And again, I like to do it in words. So we look up the specific heat in your book or chart if it's not provided for you. That's always the first step, is to look up specific heat. I included it here, 0.129 joules per gram degree C. When you're doing homework, you'll have to go look it up. Calculate the temperature change, final minus initial. The final temperature is 28.0 degrees C minus 25.0 degrees C. So my temperature change, delta T, is 3.0 degrees Celsius. Now we calculate the heat. The heat is equal to the specific heat times the mass times delta T. So that's equal to 0.129 joules per gram degree C times the mass, 5.5 grams, times the temperature change, 3.0 degrees Celsius. So we get 2.1 joules. Is that very much energy? No, that's half of what it takes to heat 1 gram of water up 1 degree Celsius. So go ahead now and just at your seats, do the problem on the next page.